All right. Well, welcome everybody to another ACE Spotlight session. Today I have Dr. George Santangelo with me. I'm very happy. I was waiting for a long time for this to happen. Okay, let me run a quick introduction. Dr. George Santangelo is the Director of the Office of Portfolio Analysis OPA in the Division of Program Coordination, Planning and Strategic Initiatives, DPCPSI at NIH. He received his bachelor's degree in molecular biology from the University of Pennsylvania and his doctorate in genetics from Yale. Before coming to NIH, George was a systems biologist and data scientist working to understand the transcriptional regulation of gene expression. He joined NIGMS as a program director in 2009 and was appointed as a director of OPA in 2011. In OPA, George leads a team of analysts, data scientists, and software developers to enable data-driven decision-making. George and his team developed the Relative Citation Ratio, a field and time normalized metric to assess scientific influence at the article level. The metric was published in PLOS Biology in 2016 and has been adopted widely by the research assessment community. Well, thank you, George, for joining us.
Thank you. Thanks for inviting me. And Ian Hutchins from my team is here as well, and actually most of the work that I'll be telling you about today is his work. So he's first author on both the Relative Citation Ratio paper in PLOS Biology that you mentioned and our most recent paper predicting translational progress in biomedical research will be the focus of today's discussion. And this is part of our efforts in artificial intelligence, machine learning at NIH, and we love acronyms because we're in the government, so AIML at the NIH is we're very happy.
Well, welcome, Jan.
Sorry?
I was just welcoming Jan also.
Okay. So just very quickly about our mission, I'll use the cursor to point. So we're mainly focused today on our development of new analytical methods. We also build tools, desktop web tools for staff to use at NIH, and everything that we do is in support of data-driven decision-making. And a big part of what we've done, I've been doing this job for 8 years now, and everyone who works with data knows that cleaning is very important. The way we like to refer to it is garbage in, gospel out. If you're using bad data and get an answer you like, it can have long legs. So it's very important to make sure that your data is as clean as you possibly can make it, and that you're doing validation and checking and making sure that your conclusions are valid. So we operate in a variety of different spaces in addition to AIML. Bibliometrics, the Relative Citation Ratio, is our foray in bibliometrics. I'll talk very briefly about that. Content analysis, NLP, is a big focus. Obviously, is very important in understanding the NIH portfolio, the investment portfolio, and then detecting emerging areas, which is something we've been working a lot on, and we'll be publishing a paper about that, or submitting one at least in the next few months. And then we have a consultation business, and we do a lot of training. So we have a relatively large team. But what we're going to focus now today is on the R&D part of our work together. Okay, so the Relative Citation Ratio metric, it was designed to meet the need for a new and validated way to measure the influence of papers. Our reviewers, our community in making judgments, and this still happens, unfortunately, have gotten into the habit of using the venue of where something's published to decide how good the paper is, rather than judging the paper itself. It's a convenience to use metrics like that. And unfortunately, though, there's a logarithmic scale for citations of papers within a journal, within any journal, including Nature, Science, Cell, the journals that are considered to be the gold standard, the highest prestige journals in biomedical research. And so we wanted to develop something that could replace impact factor, and it's starting to happen. It's a slow process, as a way of doing a quick assessment, and it's article level. That's the important part of it, is we're measuring at the article level, not using what behaviorists call a substitution heuristic, judging the paper by where it appears rather than on its own merits. And so this metric is time normalized and field normalized, and I won't be going into the details. Be happy to answer questions if someone wants to ask about it. But other than that, I won't be going into any more detail. There's plenty of detail in the PLOS biology paper, so I encourage you to take a look at that if you're interested. So I published a perspective in molecular biology of the cell in 2017, following up on the publication of this RCR paper in 2016. And there's another paper responding to some concerns that bibliometricians had about the methodology. You know, we maintain that it's still the best method that we've seen for the normalization that needs to happen to assess influence, and we do call it influence rather than impact, because that's what we believe that the bibliometric data, quantitating, looking at citation kinetics, et cetera, are measuring is influence. Anyway, this perspective in molecular biology of the cell, I made the argument that we need to go beyond just looking how influential papers are. That's part of having an impact. But in biomedical research, another important part is not only looking at translational progress and seeing the science move into clinical trials and eventually drug development, device development, guidelines for clinical practice, best practice in the clinic, and that's very important. But also tech transfer, also patenting and intellectual property and development of intellectual property. That again, that is focused on improving human health, because that's the mission of NIH. This is the main focus of what we'll be discussing today, and it was also published in PLOS Biology in October. And I'll describe what I mean in more detail about the triangle biomedicine and app scores, which are approximate potential to translate. It's our random forest approach to predicting whether a paper will be cited by a clinical trial or guideline. And then, you know, we've released in conjunction with publishing this paper, we released a new version of our tool, the iCite tool, iCite 1.0, had the relative citation ratio values. We've now added, so that's now the influence module of 2.0, and we've added a translation module which presents the data that are capturing translational progress, and I'll talk more about that. And then an open citation collection, which is making the data available free to the public, so that, you know, this is very important in the interest of transparency, to make sure that folks can calculate influence, they can calculate RCR, they can calculate the approximate potential to translate these app scores themselves. They don't need to rely on us to give them the numbers and tell them how it was done, and trust that, you know, that we're doing it properly. So, that we feel is a very important development. It lowers the barrier to entry for anyone wanting to do bibliometrics, to use the raw data to do the kinds of things that we've done, because there are lots of folks out there capable of doing similar things to what we've worked on, and you know, they've been to some extent hamstrung by the fact that it's quite expensive, has been quite expensive to get the data, get your hands on the raw data. And the Open Citation Initiative and others obviously are working very hard and doing a great job opening up the citation data for use, and we're doing it here with this Open Citation Collection for biomedical research, for the community and data set that we're most interested in. And we published a separate paper in PLOS Biology describing that Open Citation Collection and how we built that. For those of you familiar with Web of Science, it's actually more comprehensive than Web of Science, at least since 2010, for biomedical research. So, and then very quickly, a couple of other things I'll just mention that we're working on: disambiguating drug and lead compound names. Disambiguation, obviously a big issue across the board, applies in lots of different fields. I sometimes say that it's a little bit scary that we're creating disambiguation problems faster than we're solving them, but the main one being names, and we've worked a lot on that, on name disambiguation. But here we're needing to disambiguate drug and lead compound names. Lead compounds are the first identification of some biologic or chemical that looks like it has some kind of efficacy in treating a disease or in improving human health, and ultimately those need to be approved by the Food and Drug Administration in the U.S. and for use in the U.S. and that's a process that is quite elaborate. It takes a long time, but we need to be able to connect and make interoperable the FDA data and all of the drug names, and so disambiguating the drug names and the lead compound names. Sometimes pharmaceutical companies will change the name of a drug midstream when they're marketing it, and all of that. There are some concerted efforts to try and clean that. We're trying to do it comprehensively. It's been a big project, and we've made good progress on it. And I won't say any more about that unless there are questions. But then, most importantly to us, we're very excited that we're making progress on being able to predict emergence, being able to predict transformative events in science. Obviously, we're not able to do that for all transformative events, but there are a lot of them that are amenable to prediction in the same way that we're able to predict translational progress. That is the focus of our discussion today, the main focus. And then finally, we are working on a method to detect overlapping proposals. There are all sorts of barriers to sharing information across the sprawling federal government in the U.S., and so we don't have the optimal way of managing investments, making sure there's not unnecessary duplication or overlap, but even just understanding where the overlaps exist between the National Institutes of Health and the Department of Energy, the U.S. Department of Agriculture, et cetera. Having an ability to do that, and there are lots of legal and regulatory restrictions, and so we're using word embedding, we're using Word2Vec, and in combination with blockchain to dimensionally reduce the language in proprietary information so that it gets around the restrictions. So that's the last project that I wanted to mention that is in progress. And so I mentioned this publicly available web tool. Sorry, was there a question?
Oh, no, sorry, please carry on.
Okay, so our web tool, as I mentioned, allows you to track influence, track and predict, and we made this public actually back in 2016 when we first published the Relative Citation Ratio paper, and now, as I mentioned, we've upgraded it to ISA 2.0, which includes this tracking and prediction of translational impact, clinical impact, and then the open citation collection is the third module. So I want to talk a little bit about the translation module, give you a little background. And it's predicated on this idea that Griffin Weber, who's the CIO at Harvard, had about identifying translational science within what he called the triangle of biomedicine. So it's a trilinear graph, and it's based on the taking advantage of the medical subject heading terms. These are called mesh terms. So these medical subject heading terms, it's a curation effort that's been going on for a long time at the National Library of Medicine here at NIH. And what it does is to each paper, there are about 14 terms for each paper on average, and they fall under three major headings. It's an ontology, so it's a tree, and at the top of the tree that covers 95% of the terms, roughly, are human, molecular, cellular, or animal. So what Griffin realized is that you could then plot publications onto this triangle and see where they land in terms of their characteristic, whether they're more animal focused or molecular cellular focused or human focused. And the silly joke I like to tell is, Griffin put human on the right, where in IH, so we put human at the top. But it's basically the same triangle. We also fractionally count the terms instead of binary counting, which is the way Griffin did it. And that's all described in our paper. I won't spend any more time on that. But what you see here are entire journals plotted onto this triangle. And it makes perfect sense, right? You have the Journal of Molecular Biology down here at the bottom left, neurology, neuroscience. Those journals tend to be towards the animal pole because most of that work is done in animals. And then clinical research, British Medical Journal, New England Journal of Medicine, and the Journal of American Medical Association. Those are at the top where you'd expect them to be. And then there's translational research that tends to be here just below the human vertex. So that's actually kind of interesting. And this tends to be a sparsely populated region in terms of journals, but also in terms of publications. And so in some respects, this represents the valley of death that the pharmaceutical industry is trying to overcome when they try to get drugs approved by the FDA and get them into the market.
So, George, do you mind elaborating a little bit about the significance of this, and also what the term? So, basically, what I'm asking, I believe, is I imagine different articles will have specific terms. Now, you can use these terms and bring them to vector space. I think you alluded to earlier, and then use those for classification of these articles. Is that what's happening?
Yes.
Okay, sounds great. And then but you also talked about FDA, so on and so forth. And are you also trying to detect particular? So are we also concerned about the novelty of a work?
Sure, and that's part. The way to answer that, I think, is clinical trials. Everything that I'm going to talk about today, in terms of using this triangle, this trilinear graph, and characterizing and predicting translational progress, citation by clinical trials or guidelines. Clinical trials or guidelines, one can think of those as shots on goal. They're not goals, right? Scoring a goal means getting a drug approved that saves lives or reduces suffering from disorders or disease, and only a small subset of the clinical trials do that, are successful to that extent, right? So what we're doing here is measuring the first part of the pipeline, not the latter part where it's filtered down into just those clinical trials that have an impact in the clinic. I will say that we looked at the app scores and whether they capture some of that downstream information. It looks like they do. We're cautious about not to overinterpret that, but it does look like the app scores are going beyond just seeing the shots on goal. But there's more work to be done in understanding and modeling and making predictions about the entire pipeline. Does that answer your question?
Yes, I believe so to a good extent. I think so I understand this is an intermediary process, but is the goal per se to raise prominent works that can have significant impact, especially towards medicine, to FDA's attention? Is that a right assumption?
We would love that, but that would be up to the good folks at the FDA, right? Our sphere of influence, such as it is at the National Institutes of Health. So we're hoping to influence, and that's why making predictions is so important, because we're at the early stage of the pipeline, and if we can make predictions, we can help to shape investments at NIH that ultimately will come to the attention of FDA in the approval process, right? But the goal is, this is the promise of big scholarly data about doing this kind of work, is that we can, as we've demonstrated, it's early stages of this approach, but that one can develop algorithms that are successful at adding value in making decisions and understanding how science progresses, and particularly in the translational sphere, in this case, where the goal is a very concrete one of alleviating human illness.
Got it. Thank you.
Okay. All right. So, and one can address these other issues of innovation or emergence. What's likely to, what new area of research is likely to emerge from the existing areas. All those are, to some extent, they're separate questions, but they're also linked to each other, which is, I think, what you're getting at. And that's important. All that's important to keep in mind as we move forward in this process. But I think it's very clear that there's a lot of value added in doing this in attempting these kinds of efforts, in engaging these kind of efforts, and long term, I'm very confident that there will be a lot of different ways to improve, make more efficient, and accelerate progress in science broadly, but very much so in the sphere that we're focused on, which is biomedical, the biomedical area. Okay. So, this is a quick screen capture of the influence, partial screen capture. I'm going to show you a whole page. You can, folks can scroll down, and it's very interactive, as you can see the radio buttons here on the left, and one can filter, and this is the influence tab. So this is showing the RCR distribution as a box and whisker, and the publications per year, and the weighted RCR per year. Weighted RCR is simply the sum of RCRs of all the papers, where an RCR of 1, by the way, is a typical, the median NIH-funded paper, the median influence of an NIH-funded paper in any given year. So one can add that up and get a weighted RCR. And what I'm actually showing you here is work that was done by Jim Allison that was awarded a Nobel Prize. We'll talk more about Nobel Prizes in a minute, in 2018 in physiology and medicine. And it's essentially this paper, which has a very high RCR, 28. So that means 28 times the median influence, in terms of median influence of NIH, of his paper, 28 times the median NIH-funded paper in 1996, in the year that was published. So that's essentially the paper that won.
Would you mind hiding the meetgoogle.com is sharing your screen button?
Oh, yeah, I should have done that. Sorry, thank you. Didn't see the hide button. Yeah, so you can, so any paper that's in the PubMed database, and we're actually working on expanding this to include preprint servers, and including even archive, because increasingly machine learning papers that are biomedically focused are appearing in archive, and then there's, of course, bioarchive, a more recent preprint server. So we're trying to expand this to expand our reach to make sure we're not missing things that are relevant to biomedicine. But you see there are summary statistics up here at the top. And of course, everything can be exported. And I'm not going to show you the open citation collection tab, but then one could export the raw data. And we have this is fully API enabled, so the data can be downloaded for any of the modules, any or all of them. But anyway, the point is here that here we're looking at the work of a Nobel laureate, and in particular, the papers that led to actually a very important advance in cancer research. The field of cancer immunotherapy really emerged from this work and Hanjo's work in Japan, and they were the two Nobel laureates, as I mentioned, in 2018. So if we move to the translation tab, here's the trilinear graph, the triangle of biomedicine, human mesh terms at the top, and molecular cellular on the left, and animal on the right. And here is a bubble plot where the size of the bubble tells you how many papers are at that point in the on the triangle. And the summary stats at the top, you can see there are 251 papers total. 136 of them have been cited by clinical trials and guidelines. That's a very high fraction of papers that have been cited by a clinical trial guideline, not surprisingly, because this has had a tremendous clinical impact. The average app score is the prediction for what fraction of these papers will be cited, and it looks like most of them have already been cited, but there are probably a few more that are likely to be cited going forward, and the average score for the mesh terms, and it's these scores that place any given paper on the triangle. And you can see what I mentioned earlier, the sparseness of the representation in this valley of death here where the translation happens. And you can also run these as movies in the tool, and if this works, I will do it for you. So this is what it looks like. So you can see over time, starting in the mid-90s and moving through, you can see how it started with mostly molecular but also animal focused research. That was Allison's work that then progressed through the translational phase, the hard part, the valley of death, and made it into the clinic. And a small portion of the 250 papers is shown here with the citation pattern, giving you a sense that these are all linked to each other by virtue of them citing each other. And you can see the clear temporal trajectory here from the mid-90s through 2009 and beyond, when the clinical trials resulting in FDA approval of the drugs. Initially, it was Opdivo, Keytruda, and Yervoy, and now there are others in the approval pipeline. This has been a tremendously successful story in terms of curing things like metastatic melanoma and other cancers, and now there's a lot of work on expanding the scope of successes in the clinic with other types of solid tumors. That there's some really challenging ones still. Hasn't worked yet, for example, for colon cancer. But there are some successes in small cell lung cancer and prostate cancer, for example. So this shows tremendous potential. Anyway, getting back to the methodology, to focus in on our paper, and we described in terms of using machine learning to make predictions. We knew going in that total citations are a poor predictor of translational progress. So we're measuring translational progress, by the way, as citation by one or more clinical articles. We're defining a clinical article as a publication that describes a clinical trial or guideline. So that's evidence that when one of these papers is citing someone's paper, it's evidence that the knowledge has moved into the clinical domain, the clinical arena, you might say. And so in this case, what I'm showing you here is part of the table that's in the paper. It's all the Nobel Prizes in physiology or medicine from 2003 to 2015. The data publication, which is often many years earlier, that led to the awarding of the prize. It's the work that was done that was recognized. The topics here on the first column. And then the RCRs of those papers, you can see they're all quite high, some of them amazingly high, like 239 almost for induced pluripotent stem cell research. They're all in terms of the percentile, RCR percentile, they're all above 99th percentile with one exception, still quite high. And here's the total number of citations, the citations by clinical articles, and the percent of the citations that were clinical article citations. And you can see how wide the range is, right? So the number of citations doesn't give you a read on how likely it is. In the case of these, especially down at the bottom here, where they're a very small fraction of the citations were from clinical articles, whether or not those are going to be cited or not, and exhibit the translational progress. So now we can plot the probability of being cited by a clinical article on
George,
the triangle of medicine. Yes.
Would you mind if you go back? I'm trying to sort of appreciate the significance of the cites by clinical articles column. So what I'm reading is RCR. So could you elaborate once more? I'm trying to appreciate. So from what I understood from what you said is that RCR gives you a more reliable sort of measure to see the translational progress. Now, could you elaborate a little bit more on the table that I'm seeing and relating it to that point?
Yeah. So RCR does not. All RCR does is field normalize and time normalize the total citations, right? So if you look at the publication date, we've got a wide range. We've got a paper published in 2007. We have other papers published in the early 80s or even late 70s. And so the total citations needs to be normalized, so you need to look at citations per year. I'm not showing you that here. But RCR does that, right? So that's one thing it does. And then it also takes into account what field it's in. For example, MRI is an imaging method. It's an engineering advance, essentially, whereas vesicle trafficking is heavily looking at how proteins are moved around cells, is a heavily molecular and cellular topic. And so you'd want to normalize to the expected citation rate in those respective fields, and that's all that RCR does. So there is a correlation here. If you look at the RCR on the total sites, you can get the general sense that they're correlated, but it's not a perfect correlation, and the extent that it's not perfect reflects mostly the fact that these are different fields, and we're normalizing to the expected citation rate for the field that the paper is in.
Got it.
Okay, and then citation by clinical articles is a different take on citations, right? It's looking at how relevant to clinicians. So some papers that are cited a lot are very relevant to clinicians. This Helicobacter pylori, the fact that this infectious agent is causative for ulcers and gastric adenocarcinoma, for cancers, has been tremendously important in the clinic, and so that's why this number is so high. Other things have not fully manifested as having clinical impact, and so those are at the lower end of the scale. So that's very different from what you see in terms of the distribution of total citations or the RCR values. And that's what I'm showing here in this last column, is this heat mapped distribution of the percent of total citations that are represent interest by the clinic, by clinicians in the work.
Thank you for the elaboration.
You're welcome. So then plotting, we can plot the likelihood that a paper will be cited by a clinical article on the triangle, and you can see it's clearly non-uniform. And here it is after 2 years, after 5 years, after 20 years. And you can divide the triangle into thirds, and that's what's plotted over here on the right. The high, the medium, and the low end of the triangle. And this is my former area of research, molecular and cellular systems biology. I'm a recovering systems biologist. So that you can see this is very cold down here. So it's very hard to do molecular and cellular research that ends up having clinical relevance. Animal research is a bit better, and human research starts out being closer to the clinic, of course, and so it's more likely. But notice that the hottest area, this is the scale here, so the white is the hottest area, that area is below the top. So it's not fully human research. It's got some molecular, cellular, or animal, or both characteristics, the papers that have the greatest potential to be recognized as important in the clinic, which is interesting. But you can see that for all parts of the triangle, the kinetics are practically identical, right? So in all cases, you've got this kind of sigmoid pattern that represents the trajectory of interest or knowledge flow, you might call it, over time. And what we found is that essentially by 7 years, you've gotten most of the transmission of the information into the clinic that you're going to get for any of these categories. Okay, so now we get to the machine learning piece. We used a total of 22 features to feed into the machine learning. And HAMC simply refers to those mesh terms, right? The H is human, A is animal, MC is molecular and cellular. And there are also other mesh terms that are relevant to this effort. There are mesh terms for different diseases, there are mesh terms for therapies, and there are mesh terms for drugs. Those are outside of the ontology, the HAMC ontology, so they're modifying mesh terms is the way they're referred to. And so those are relevant too. So we we played around and found that those were adding value in terms of predictive value, and so those are incorporated. In this case, what I'm showing you up here are the summary stats of the papers that cited the article for which you're trying to make a prediction. And then the article itself, we're incorporating those same features, but also the frequency with which it's been cited, normalized to how long it's been out there. So how many years since it was published. So citations per year, as I was mentioning earlier in terms of talking about RCR. So we're using the properties of the features associated with the article itself and the properties of the papers that cite that article to feed into the machine and try to predict with information captured early on after a paper's been published, whether it's likely in the future to be recognized by clinicians as relevant to their research.
As you can create.
Are there any questions about this? Because it's really important to understand the features that we fed into the model.
Yeah, that sounds very interesting. I think if you could recap as to so it seems to be either a neural net or any classification algorithm or a regression algorithm that would output. So you know what? Let's start with that. Are you looking at it as a regressor? Are you getting a continuous value out of this model?
Right. So that's on the next slide. So we we trained a machine learning model with a variety of different ways. We did use logistic regression. We tried everything that was available. And found that random forests actually outperformed the rest in terms of holding out a test set and measuring generating ROCs or F1 scores for the model. So random forests work the best. So that's what we settled on. That's also nice because it's possible with random forests to output the importance of the features in contributing to the accuracy, right? So
also into data types, right? If you have they require less pre-processing, less normalization because they're a decision tree. But a quick question, I think, regarding to your last slide, perhaps. Then, so is it? I'm trying to recap the goal, seeing if I understand it correctly. So basically, you have a set of features, be it time, year, or content features from the paper, and you're trying to predict if it's going to be cited by a specific target, cited in general. Which one is the goal?
So the goal is to determine whether it's cited by a clinical article, right? So whether the outcome is whether it's cited by a paper describing a clinical trial or a clinical guideline. So there's a specific type of article. So there are flags in the database, in the PubMed database. The National Library of Medicine curates and adds those flags. So the publications are sorted into different types. And so the clinical article is the one we're interested in here because we want to know, as I showed you for these Nobel Prize winning papers, the likelihood that it's going to, any of these papers in real time after they're published, right? These are all very old, most of them are pretty old papers. But, one can imagine if within a couple of years after these were published, if we could make a prediction about whether they're going to be cited by a clinical article, that's very different from just predicting how well cited they're going to be, right? We're looking for a specific class of citations, which indicates translational progress, movement into the clinic. The knowledge has proven to be of interest to clinicians doing research to try and get closer to improving human health, translating bench-to-bedside, as it's called, translating the information into things that actually move into the clinic, which, of course, being a public agency, a government agency, we're spending taxpayer dollars. Taxpayers are less interested in academicians getting publications and advancing their careers. They're giving us the money to spend on improving human health, right? So having an impact on diseases that are the source of loss of suffering. And so this is important in terms of the mission of the agency. It's an important facet of what we're doing, and one could argue that's true for any agency, right? So Department of Energy, one of the goals is to address climate change by improving the source, moving away from carbon-based energy generation and alternative sources of energy. And so that's an outcome there that you'd want to just publishing papers that that address fundamental research in energy generation is not of no worth, but it's of less value than something that looks very promising in terms of moving into practice, into actual engineering to address a problem that's affecting all of us, right? So that's the idea here, is to make predictions that improve our ability to make decisions, because they give us a window into the future of what looks promising, what areas of research and what publications in particular are likely to bear fruit in improving human health.
That's amazing. One last clarification question. Sorry to hold you up on this, but
no, it's quite all right. Yeah.
So just want to, for a machine learning inclined audience. Just let's take a look at your feature inputs. So are they? You have the. Okay, there is the trainings article citation. Oh, could you point to the input features, please?
Sure. So the article stats are these here, outside of the citations per year, which is the citation rate. That's this one. And well, I'm sorry, the article stats, sorry, I misspoke. The article stats are these here, and the citing article stats are these. It's actually the max, the mean, and the standard deviation of the HAMC, the human, animal, molecular, cellular. And the mean and standard deviation for the disease therapeutic mesh terms and the drug mesh terms. So that's wrapped up into this box here. So the article stats are these specific ones associated with the article itself. And then the citation rate is simply how many papers are there in the citing network, right, per year. How many papers have cited that paper? That's the middle box. Right. So that's our training set.
Or papers in general, or only the clinical trial paper?
This is all papers. Right. So it's all papers and all papers that cited those papers, with the exception of the test set, which is held out for testing, right? So, and it's all the papers that are between 5 and 20 years old. So, we're starting with papers in each year that are either 5 years old or up to 20 years old, and using those, entering those into the system, with the outcome variable being the citation by a clinical article. And then we get our model that then we test and see how well what the performance looks like. And that's where we tested a bunch of different approaches, and random forest performed the best, and the rest of what I show you will be based on the random forest model.
Nice. So just to give you, partially my fault, but just to give you a heads up for the time, we got 14 minutes.
Yep. So, yeah, I think we're in good shape. So in terms of the validation, it turns out we can make accurate predictions within 2 years after publication. And you can see the receiver operator curves here for just 2 years worth of data, or all the data. So 2 years obviously doesn't perform quite as well as all data. And as I mentioned, the peak is at 7 years. After 7 years, we get very close to this curve with all the data. And here is a precision recall graph relative to chance, either for 2 years worth of data or all of the data. And then the final graph here shows that there's a very strong correlation for papers published in 1995 or 2000 or 2005, so roughly 15 years old and older. Those papers, essentially all the information is in that we can use to make predictions, And so the predictions shown here on the x-axis correlate really well with the actual data in terms of the paper, whether the papers were cited by clinical articles or not. The fraction of papers that were cited. Okay, so that's the first level. The second level of validation was to compare it to expert ratings. So we had some data already from experts in the intramural program here at NIH, who are in, spread across all of the disciplines of biomedical research, and they were kind enough to help us out by rating papers in terms of their clinical impact. And this is the result of their input, and here's the machine learning result. So actually, it looks like the machine outperforms the humans in this. We interpret this very cautiously, though, because experts, of course, may be using other inputs the machine doesn't have access to in making those decisions. So we don't call the machine result ground truth here, but it's just interesting that that it did. It certainly did at least as well. Machine did at least as well as experts in determining the clinical relevance of the papers. And here it is there's the ROC curve on the left and precision recall on the right. Okay, and then a couple of other things that we included in the paper were we didn't want folks to overinterpret the scores, the probabilities of whether a paper is going to be cited or not. And so we stratified them, right? So we used 5 different categories: 5%, 25%, 50, 75, and 95. It's the reason we call it approximate potential to translate. We want to make sure that people don't overinterpret, and giving someone a number like 21.9 might cause them to overinterpret. So if we roll those up into these broader categories, then folks can really understand, in addition to the title of the metric, approximate potential to translate, that these are rough categories. They're not, the precision is not high. So, and we tested to make sure the scores were stable, because that was important. We want to make sure that they're not jumping all over the place as time goes on, because that would be concerning. And they are very stable, though you can see they can change over time, and largely what happens is they increase mainly the changes from this 5% category to the higher categories. In other words, as time goes on and papers are cited more and more, some of them at least move into a higher category, but then that plateaus. You can see that it stabilizes. As I said, after about 7 years, we've got about all the information we're going to get from the information that comes from people citing those papers, and then the categories are pretty well locked in. The other thing that is very interesting here is Ian did a very interesting thing with with testing the performance of the machine learning system, in that we wanted to know whether, if you trained classifiers over time, that is, you used information in different years to train the classifiers, versus use a fixed classifier and just add the information over the years that comes in as papers are cited more and more, that could distinguish between some kind of baseline change over time. In other words, we're trying to explain what's happening when additional time goes by, up to 7 years, and the performance of our system gets better and better and plateaus at 7 years. What's actually happening there? Is the classifier identifying baseline changes in the entire landscape of biomedical research, or is it simply information specific to those papers as they're cited that is contributing to the changes in scores, and mainly the movement of the 5% category to the higher categories, for example? So we looked at that, the change in the app score, with a fixed classifier, which is the orange, or a fixed citing network, which is the blue. And you can see if we fix the citing network, it's flat. Nothing happens. The change hovers around 0. So there's really no change in score when we fix the citing network. But when we fix the classifier, that's where you see the increase. So this says that there aren't baseline changes, that the changes are coming from additional information that's coming into the system as the papers are cited over time. a little bit complicated point, but I think it's a very important one because we need to know what to the extent possible, we need to know what the machine is using is keying off of as it generates these outcome predictions.
Mm-hmm.
And then finally, being a recovering systems biologist, as I mentioned, a molecular geneticist, I'm very fond of this experiment, which is to do a genetic analysis, genetic in quotes, of the machine learning predictions of future translations. And what we could do there is take the actual citing papers after 2 years and, and then mutate the third year's worth of citations. So what's shown is on the top line here are the actual citing papers. So 2 human papers, 1 human animal, 1 human molecular cellular, and 1 with all 3. This is just as an example. And so this is a starting input, and then the citations in year 3 that we can change artificially, just engineer that ourselves to change it to all molecular cellular, all animal, all human, or human plus. Human plus is human plus one of those modifying terms that I mentioned, disease, therapeutic, or drug mesh terms. So that's human plus, is human plus one of those. Mm-hmm. So in doing the mutation, we could start with papers that are, look at all the papers, or we could divide them into ones that are at the human vertex, at the animal vertex, or at the molecular cellular vertex. So they're starting at different places. In terms of the location of the paper being cited, that we're measuring the approximate potential to change and the approximate potential to translate. We're starting with papers here that all start at 25% in terms of their app score, and then are moving up after the year 3 citations. And so you can see here that all of these, this is the extent to which they move up after the year 3 citations in the actual data, the original pattern of citations. And then when we engineer them to be all molecular cellular citations, actually the potential goes down, which is a little bit disturbing as someone who did this kind of research. But then if it's all animal, so this category, then it has a variable result, which is actually quite interesting, right? If you add animal citations to a molecular cellular, a paper that starts out being at the molecular cellular vertex, it actually causes the app score to go down a little bit. But if it's an animal paper, it causes it to go up. So there's a difference based on how the paper started out, which is interesting. It's a reflection of the domains of knowledge and how the flow of information is happening from these areas of research into the clinic. And the same is true when we add human terms. It helps the molecular cellular papers when they're cited by human papers more than if they're cited by animal papers, for example. And the human plus paper citations did the best, though the molecular cellular class is helped less than the actual naturally occurring citation networks. So this is informative, and it allows us to conclude that the knowledge is percolating through different domains in order to reach the clinic, which is interesting. We can actually see some of the nuances of how that's happening with this experiment. Okay, so just summarizing very quickly, in the time we have left, our office develops tools, web tools that can be accessed by decision makers across NIH, so thousands of decision makers that are distributing investments in biomedical research across the scientific community where it's relevant to the NIH mission of advancing scientific knowledge that improves human health. And so we develop tools and deliver them to the community. We also, and in some cases to the public, as in Cite 2.0, the tool I mentioned that's publicly available that has the 3 modules, influence, translation, and the open citation collection. We also develop new methods, including AI/ML approaches to improve data-driven decision-making. The one I focused on to describe to you today is the one that predicts translational progress in biomedical research, and that has the potential to accelerate scientific advances and improve human health because we can learn about what in the literature has the greatest potential to move into the clinic. And then we did that by building and validating a machine learning system that accurately determines within 2 years post-publication. So it's a lagging indicator, but it's still early enough that it gives us information that we don't have without the machine learning approach. The likelihood that any or all papers, and we can measure all papers in the PubMed database, whether they'll be cited, likely to be cited by a clinical article, a paper that describes a clinical trial or clinical guideline. And those making those accurate predictions requires both the features of the paper in question and the features of the papers that cite it, as I described for you. And so analyzing, and then finally analyzing citation patterns, as I just showed you with the genetic experiment, indicates that knowledge flows through different domains before percolating into the clinical arena. So again, I thank you for inviting us, and if there are any other questions, be happy in the time we have left to answer them.
Absolutely. So we got around 6 questions, and we got 2 minutes. Would you mind staying a few minutes over, or should we cut it sharp at 1 p.m.?
No, I'm happy to stay and answer all the questions if possible. Yep.
Okay, sounds great. Then let me go through them in order. So the first one was that our audience already found a package in R for your score.
Right.
They're asking if there is a Python package available, because we like Python.
Yeah, of course.
So there's not currently a Python package available, but that's something that we can consider generating in the office here for the external community.
Amazing. And if you share that with us, we'll share it with our audience as well, publicly.
Great. Yeah, that's an important. I'm glad, because I didn't mention that in addition to making the raw data available, we also make the code available so that folks can reproduce what we've done.
Mm-hmm. So as you know, so we on the website we can post the website. We can share the code as well. We can coordinate with that maybe after the call via email. Make sure everybody has access to it. If you'd like, we can add the packages link as well on the website so that they can access.
Sure.
All right.
Sounds great.
Wonderful. All right. So so we had a couple of interesting questions. So I think this is a clarification question. They asked if you figured out what was the most relevant feature. I think what they're asking is what from the features that you were using, did you happen to notice a feature that's contributing the most?
Yes. So that was unfortunately I didn't make a slide of that, but if you look in our paper, there's a table that I think it's table 2. Yeah, table 2 has the full list of the rank of features, but just very briefly, I can tell you that it actually differs for the different kinds of articles. For all articles, the citations per year is the most important, but then next is the mean of human mesh terms, and after that is the standard deviation of human mesh terms, and then the mean of disease terms. So the full list is there in the table. But for fundamental articles, so for example, articles that start at the molecular cellular vertex that are very focused on molecules or cells and not humans, the mean of human mesh terms was the most important. So it differed between fundamental articles and all articles or human-focused articles in terms of what features were important. And that, again, supports our idea that knowledge is flowing through different domains before it reaches the clinic. And so hopefully that answers the question. But yeah, that's the really great thing about using random forest. It's probably in some senses the least sexy of the machine learning approaches, but it did outperform the others and gives us these outputs of importance rank.
Mm-hmm. Yeah, absolutely. And as you mentioned, it uses information gain. You can extract confidence, right? So I think the next question is, did the human agents use the same definition of relevance? In other words, this relates to the comparison that was made post hoc after the evaluation was made by the machine and human and was given to experts, I believe. In other words, what was the question that was asked from the human experts?
Yeah, what the question was, how likely or how likely is this work to have clinical impact, right? So the question wasn't exactly the same, wasn't a perfect match what the experts were assessing. And in any case, one needs to be very cautious about interpreting. We didn't ask them in great detail how they were, in any detail, in fact, how they were making their judgments. So it's hard to know for sure. And different experts, of course, could have been using different criteria to make their decision, ranking it from 1 to 5, how likely it is to have clinical impact. But that's what we asked them, and that's what we were comparing with respect to the machine learning system.
Got it. So let's spend a minute or two then, I think the final minutes on the sort of the feature and representation learning of field classification. So far it seems that you have a process like the triangles you were showing earlier on that brings the words used into a distribution. Were you using actual word vectors and embeddings as well, or it was mainly the first order stats?
Yeah, it's just the mesh terms. Yeah, just the assignment of terms, not any embedding of text. Just the mesh terms.
Are you considering in future research perhaps so there are, I think, 2 areas that are I think it's one area in natural language processing and deep learning that relates to this I'd say closely, which is so at the first stage perhaps we could bring the words into a vector space and just have that as a sort of richer representation of the articles, domain-specific representation. Something like word2vec or glove, some shallow representation, and a more, I'd say, advanced version of it nowadays is language models that try to, or reading comprehension algorithms that try to bring an entire piece of text to a vector representation as a rich feature set. As compared to first order stats. Is that a direction you're considering?
Yes, absolutely. And in fact, we just had a presentation on Monday of looking at the app scores with a variety of different embedding approaches, including word2vec and Cybert and others. And that's definitely it's a great point. There are definitely potential improvements that we can bring to bear now that we have the basic framework of and knowledge that this adds value, that we can generate accurate predictions. Testing, and as you and your audience are aware, this is a rapidly moving area of research, and as it continues to improve, we'll continue to try to stay abreast of it, and test out the different approaches that are possible to improve performance and give us a better and better read, and maybe even getting back to the question you asked at the beginning, narrowing down, not just predicting shots on goal, but actually predicting the goals, right? So predicting what's going to actually result in an FDA-approved drug, for example.
I'd say on a relevant note, I had a similar work a few years ago, and not in purpose actually. So this is on term extraction, automatic term extraction. Do you think those systems could help? Basically, systems that would extract terms that you think are relevant. Are you using already existing tools right now?
Yeah, so we have been working for a long time on extracting mesh terms, And so we use those in the paper. It's not very prominently described in the paper, I don't think, but it's definitely something that we rely on heavily, is extracting. We can also extract mesh terms and associate those with grant applications and awards, right? That's something else that we've done for different projects in the office. So yeah, that's been quite valuable in enriching the feature space for the mesh terms.
So, and in the past, I know mostly relative frequency measures or specificity scores and measures were very prominent in the area, and they're very solid, and they usually don't need any training for automatic term extraction. The article that I'm referring to, it's a distributed specificity score, basically, as opposed to just some relative frequency measure. We're looking at local and global vectors. So in the local vectors, would represent a specific the specificity of the term and how it behaves. It's a word-to-vec model on the specific technical documents, and then you have, for the same word, you may have a representation that's more generic, and if you concatenate and put them together, it's a very strong indicator if a word is a term. Now, I'm not exactly sure if it's going to be super useful, but I'll be more than happy to share it with you.
Yeah, great, thanks.
All right. Well, that was my final question. If you have any final comments, George?
No, other than, well, thank you again for inviting us. I think, we're really excited about the potential for others to embrace these kinds of approaches. And, at NIH, we're very enthusiastic about seeing work in this field from anywhere that can help us to improve these kinds of methodologies and add value in data-driven decision making, so that we can do better and better at identifying the kinds of science that move into the clinic and ultimately improve human health, and a variety of other kinds of projects that we work on that are valuable just broadly in terms of and illustrate the value of machine learning, of AI, ML types of approaches in a practical setting. And so, in fact, anybody in your community that's interested in reaching out to us and discussing these kinds of issues further, we do have from time to time open slots. If folks are interested in joining us, that's another possibility we could talk about. But just in general, seeing the area of science expand and demonstrating the value of this kind of research with practical applications is something that we're very enthusiastic about.
Oh, absolutely. So 2 points. One is that I do believe it's a very prominent work. Information is going to become, it's already overwhelming, and in our field, deep learning, it's very, very hard to actually track, even for the experts, what's coming out, what's significant, what should be, what will have a more longer term impact, as opposed to incremental, which I think relates to your point. What's actually going to translate in our sort of field? We're very much concerned with, at least I am, with the industrial application, right?
Right.
Is it translate? This is a question that's been asked every day, and thanks to your research and people in your field, we have now a better metric to assess that. And of course, I believe our community is more than interested. Let's chat later on. I'll definitely communicate, see if there is something that we can work on, or aside from that, if anybody is interested, feel free to reach out directly to George or to us if you'd like. and we take it from there.
Sounds great.
All right, amazing. Thank you for joining us, George and Yan. It was a pleasure having you. I'll talk to you in a future event.
All right, likewise. Thanks very much.
Thank you.
Everyone for joining.